Hi, in this video I am going to discuss the theory behind the random forest model. The course outline for this particular session is as follows. We'll start with the basics of machine learning model. I'll talk about what machine learning models are, and then what are tree-based models. Machine learning models are of many different types. One of the type is tree-based modeling, and we'll see what these models are. And then we'll see what is bagging and random forest. Bagging is a type of model which is very similar to random forest. So we'll do a comparison, and then we'll take an exercise using R where we'll build a random forest model and compare it with other models and see whether it is good or better than the other models or not. And finally I'll give two exercises for you to solve on your own. Okay, so what are machine learning models? Well, machine learning models primarily are of three types. Okay, one is supervised learning models, the other one is the unsupervised learning model, and the third type, which is not very often we come across, is the semi-supervised learning models. Most of the times we come across the first type of models, which is known as the supervised learning models. The other two, unsupervised and the semi-supervised, are the ones that we rarely come across. Although in the recent times there is a lot of interest in unsupervised learning, and people are popularizing this model as well. Okay, so what is supervised learning model? Well, supervised learning models are the models in which your data set has a target variable in place. So your algorithm will get to know how the target variable looks like. So here is an example. Okay, you have got y, which is a target variable, the variable that you want to predict using predictors. And there are different predictors, x1, x2 and x3. So using x1, x2 and x3, you are trying to predict y. So the model is able to see in the first hand that how the target variable looks like. Okay, so that is supervised learning. On the other hand, in unsupervised learning, you do not have a target variable. The one thing that you have is your predictors. Okay, so in that case, it is not going to be able to give you which category a particular data point belongs to. All it can give it is only different categories without labeling them. Okay, so this is a label, right? This is the label. Whereas here you cannot label the data. All you can do is simply categorize into different black boxes, that yes, this type, this particular type of data is one type, and there is another type of data. So there is no labeling as such, or there is no target variable as such. So this is unsupervised learning, where the model tries to learn only from the predictors without looking at the target variable. On the other hand, semi-supervised learning is a case where you have a mix of both supervised and unsupervised data types. You have got a target variable for few observations, but not for all observations. Okay, in that case we call that as a supervised learning. So basically in machine learning you will come across these three type of problems. So we'll only be interested in supervised learning, okay, for this video. Okay, so random forest is a supervised learning model, so we'll only take into consideration the supervised learning type of problems. Okay, supervised learning can be of two types. One is regression, the other one is classification. Okay, so regression, I mean, those who are familiar with these concepts, I'm sure this is very simple to understand. Those who are not familiar, a regression problem is where your target variable is continuous in nature, whereas a classification problem is where your target variable is categorical in nature. Okay, so this is a typical case of regression problem, because the target variable is continuous. Whereas had it been just 0, 1, 0, 1 or something like that, it would have been categorical, right? So that's classification problem. Now how do you build a learning model? Well, you provide training data and then you build a machine learning algorithm Using that algorithm, you apply your algorithm to new data which does the prediction. So the idea is and this is primarily for supervised learning, where your training data has your target variable in place. Your learning algorithm learns the pattern or the relationship between your target variable y, which is a function of your predictor variable, right? So that's the idea. You just want to come up with an equation that can be used to predict your new data, right? So that's the idea behind building the model. Now, classification and regression problems can be solved in many ways. Okay, you might have come across algorithms like linear regression. Okay, and classification can be done by logistic regression. These are popular and simple linear models. However, we'll talk about a type of model known as the tree-based model. And one of the popular and the most popular tree-based model is the decision tree. Well, decision tree is different from the regression model from the fact that decision tree is more non-parametric in nature, and this is just a jargon. Don't be afraid of what non-parametric is. Well, non-parametric is just that you do not estimate an equation. You do not have, alpha, beta, so to say. Okay, like in regression, if you're familiar with regression, you have always alpha, beta, right? Intercept and slope coefficients. You do not have such parameters to be estimated in decision tree. All we need to do is just to partition the data and use some sort of a technique to find out what could be the potential value of a particular observation in future. So it's very simple. So here is an example where your x1 and x2 are predictors. So you divide your data based on the values of your predictors, and then you find out what is the final value. The final value, let's for instance, is a classification problem of 0 and 1, and then yes, this group it is 0, and this group this is 1. So somebody falling in this particular group is 0, somebody falling in this one is 1, somebody of this here it is 1. So the idea is simple. You partition your data recursively and then take the majority. Okay, if there are, let's say, 3 0 here, let's say 4 zeros and 2 1s, then we consider this particular segment to be having classified as 0. Okay, let's say we have 3 1s and only 2 0, the majority is 1, right? So the final value is 1. Here in this case we have also majority of 1 and 0 is the minority, so we just took the maximum count and the value is 1. So that's the idea of classifying your data using a decision tree model. If you're not familiar with theory, I recommend you to go through one of my video on decision tree theory, and it's there in the description section. The link is there in the description section of this video. Please go through that video. You will get a better overview. The same thing can well be done for regression problem, except the fact that you do not take the maximum value. Finally, you just take the mean of all the observations. Let's for instance, in this particular segment, there are 4 values: 4, 5, 6, 6, and 6. Okay, so there are 4 values. Okay, so the total is or the outcome is just the mean of the 4 value, and mean is your how long, 21 by 4, which is 5.2. 5 point yeah, it could be 1 or 2, something like that. Okay, so 5 point something. So the idea is you can just partition your data and predict the value, whether it is a classification problem, whether it's a regression problem. It's very simple. However, the problem with decision tree models are quite a lot. It's very simple though, but it doesn't capture the nonlinear relationship with your data very well. And there are many other problems as well. A decision tree model has a problem of low prediction accuracy and high variance. High variance as in if you change your data, it is the prediction accuracy is going to vary a lot. Okay, so prediction accuracy is going to vary, and that is not a good thing. Not at all a good thing. Okay, So we want models that has less variance, in the sense that if you use 10 data sets, the prediction accuracy should be very consistent across these 10 data sets. It should not vary much. If it varies a lot, then who knows, your model will predict well for your new data or not. That is going to be a problem. So in order to overcome these two problems, we combine many different decision tree and come up with a new tree that is more efficient than a single tree. So we use multiple decision trees. Okay, so we combine the output from multiple decision trees, and that would reduce the variance. That would surely reduce the variance, and we call that as ensembles. Okay, you might have heard ensembles in many other different areas. Ensembles is nothing but combining different pieces of work and then coming up with a really good thing. It comes from the field of music, right? In the field of music, you have many different instruments, like you have drums, you have guitar, somebody is a singer, and then you have tabla player, and then you have somebody playing violin. Well, each one of them is playing their own part, but when you combine them in some sort of way, the combined output is better than the individuals, right? So that is the idea behind ensemble. So you build different models, combine them to ensure that the prediction accuracy is higher than the the single model. So that's nothing but ensemble learning. The idea is to combine weak classifier, a single classifier, a single decision tree. A single decision tree is very weak, okay? So we need to combine them in order to make them stronger. And there are many ways of combining. One of the way is bagging, the other one is boosting, and the third one is random forest. And that is the topic for this session, where we'll try to understand the idea behind a random forest. We'll not get into the mathematics of behind random forest. So I'll keep the mathematical part as simple as is possible, just to understand the intuition behind random forest model. Okay, so the idea is that you combine multiple decision trees. So instead of just one tree, just have multiple ones, okay, for the same data, okay, and then take some sort of an average for all the models that you have built, and you use that. How do you know how many trees to be built, right? You have said many different trees. How many trees? Okay, let's say that value is n. How do you know what is the optimal value of n? How many number of trees is to be created or generated in order to find the best classifier? Well, you just take if you're using this model for regression problems, then take the help of square of the error or the mean square error as one of the metrics to evaluate how many number of trees are to be used finally. So what exactly is the value of n? If it is a classification problem, then take Gini index or deviance. Okay, that's the matrix for classifications. So that's how you come up with the optimal value of n. So let's understand bagging first before going to random forest, because bagging is the foundation of random forest. So it's always good to understand bagging first. There is a video in my channel on bagging where I have explained theory and application using R. You can go to that video. It's there in the description section of this video. I'll just briefly explain what bagging is. Well, in bagging is otherwise known as bootstrap aggregation. Okay, and bootstrap is a very popular technique where you take a subset of your sample randomly. So you have a sample, and there are data points here. You just take a subset of it randomly. Okay, let's say there are 100 observation inside. You just took 60 observation randomly, and you created one sample 1. You take another 60 observation randomly, and you created random sample 2, 3, and so on. That's called bootstrapping, where you randomly picking observations. Okay, but remember, you are picking observation with replacement. That means the same observation can be picked twice. Okay, That's the idea. Okay, let's say you have 100 observations with all unique, like 1, 2, you know, up to 100. Okay, whereas when you're picking observations in your random samples, you can have multiple value for the same number. We can have 2, we can have 4, 3, and so on. So the idea is that the observation should be replaceable or should be replaced while picking up. Okay, so now you understood what bootstrapping is. So bootstrapping is used in bagging. There are 3 different steps we follow in bagging. In the first step, we create bootstrap samples. Okay, and if capital N is the number of observation in your main sample, in the bootstrap sample you will have lesser number of observations. You can have the same number of observations, but good to have a lesser number of observation with replacement. That's the main point to be noted. Okay, so we can have multiple observation from the main sample in your bootstrap samples. Okay, because that's each observations is replaced once it is selected in the sample. So you have multiple bootstrap sample from the main target data or the training data, and then you train learning model, and you can use any learning model, but we'll only talk about decision tree here. So you build decision tree model separately for different random samples. Okay, so if you have let's say you came up with 10 different bootstrap sample, you will build 10 different decision tree model in separately for each one of these data sets. Okay, in the step 3, in the final step, you do the final prediction for this particular data set. Okay, let's for instance you took 3 bootstrap sample. Okay, and this is a classification problem. So the first sample predicted, or the first model predicted that the observation 1 is nothing but it's 1. The second model predicted it to be 1. The third model predicted it to be 0. Okay, so this is observation number 1. Observation number 2 is predicted to be 0, 0, even by the third model 0. Now observation 3 is 0, 0, and then it's 1. So what is the final one? The final for this particular observation, because there are 2 ones, right? So the maximum vote is 1. Here there are 3 zeros, so it's obvious it is 0. There's 2 zeros, only 1, right? So the majority vote is maximum count is 0, so it is 0. So it's the classification problem. Take the majority vote or maximum vote. Okay, right? And remember, the number of models you're using could be lot more. It cannot be just 3. It would be over hundreds. So that's the idea. Okay. Now, in the case of regression, you just take the average of it. Okay. So if it is regression problem, let's say it's the first model predicted to be 4, and then second model predicted 4, and the third model predicted 5. So the average is 5 plus 4 plus 5 by 3, which is 14 by 3, which is something like 4 point something, right? 4.6. So final value is 4.6. So the idea is you are using multiple models now, the output from multiple models, not just one model. How is random forest different from bagging? Well, in bagging we have used random samples, right? The word random is important because these samples are purely random. It's not something that you have selected on your own. That's the idea. And the idea behind making the sampling random is because the variance is going to be better. There is not going to be overfitting. It's not going to be overfitting. And the variance of the output or the prediction error would be less. Okay, so that's the idea. One of the main difference between bagging and random forest is that bagging uses the full set of predictors. you have 10 predictors, 10 independent variable or predictors. Bagging is going to be going to use 10 of them while splitting your data and while building separate models for this bootstrap samples. However, random forest uses only a subset of them. Random forest uses a random subset of them. It doesn't use the entire set of predictors. It just uses a random subset of them each time. So out of these 10 variables, let's say it selected randomly 6 one of them for first model, another 6 one of them for the second model, and so on. Okay, so the idea is to use the best set of predictors each time rather than taking the entire set. Okay, and that is supposed to improve the randomness. Okay, so we talked about random sampling, but even the variable selection should also be random, right? Variable selection should be random, and that exactly is the main differentiator for random forest with respect to the bagging. So random forest uses a random set of predictors. The random is again, so there are two random things here: random sampling and random selection of variables. So this is even better models on theory. Okay. Now whether this is going to improve the prediction accuracy is something that cannot be guaranteed, but in many cases it is definitely going to improve the prediction accuracy. So question, what is the optimal number of predictors to use? How do we know that 6 variables or 6 predictors is to be used from 10? Okay, so the thumb rule is that if it is a classification problem, then the number of predictors that you should use is square root of k. K is the total number of variables. Say in this case, if it is 10, then you should use root over of 10, which is equivalent to 3. And if it's a classification problem, so if it's a classification, it's a square root of the total number of predictors. If it is a regression problem, it's just the 1/3 of the observation predictors. But you can always experiment. You do not necessarily have to go by this thumb rule. You can experiment with other value of m, other number of predictors, and you probably get a better results. Now bagging is a special case of random forest when m is equal to k, right? Because bagging uses all the variables, right? All the predictors. It doesn't use a random subset of them. Hence, bagging is just a special case of random forest. Random forest uses a random subset of the entire number of predictors. So, when m equal to k, it's just the case of bagging. Yes, so that's what we talked about. There is additional randomness. Not only we have randomness in subsampling or bootstrap sampling, we also have randomness while selecting the predictors, and that will reduce the variance. And it also works well on smaller sample data. Bagging doesn't work well on smaller sample data, whereas random forest has a better performance. So that's another advantage. So what are the steps involved here? Now we understood what the steps involved in bagging. The first two steps in random forest is exactly same as what we have learned in bagging. In the step 1, you select bootstrap samples with replacement from the training data. In the second step, you train the model for each the samples. Decision tree is what is going to be used in this case. So the first two steps are exactly same as what we have learned in bagging. The third step is different, or it's an additional step. Select m predictors out of k predictors. So total number of predictors are available to be k. We are going to take the m predictors randomly, okay, for using for building the decision tree model for these different samples, okay, and that will vary with respect to the samples, okay. Now that's exactly is the difference here, right? This third step wasn't there in bagging, so this is an additional step. When you build a model, you may not use this, there will be default values, and you can always have the control over the default value and see which one is the best one. So prediction purpose is the mean of the for the regression problem, it's the mean of the regression value, and for classification it's the maximum mode. That's what we also have learned in decision tree and bagging. The rule applies, the same rule applies in random forest as well. A few questions you might ask yourselves. How do we choose the splits? The same, it's very similar to what we use in decision tree. We use mean square error for regression, and we use Gini index or deviance for classification. Okay, so these two metrics are used to find out the optimal value, optimal number of predictors to be taken. Okay, how do we select the number of trees? Okay, we talked about number of trees in bagging. How do we select the number of trees in random forest? It's similar, very similar. Okay, you just go on building different number of trees by taking different subsamples or bootstrap samples from the main training data, as long as there is no change in the error. Okay, when there is change in error, you go on building more number of trees. Okay, whenever you see there is no change in the error in your data, then you stop there, because then increasing more or adding more decision tree is not helping improving the prediction, right? So that's where you need to stop. How to select the optimal number of predictors? Okay, so you can try with the default, and then you can increase and decrease and see what is optimal. The default may not work well all the time, so just increase and decrease, do a trial and error, and you might get a better result. So we'll take an exercise and we build a random forest model using R. If you haven't downloaded the random forest package, you should install it first in your system. And once you have installed it, you should load it. First, you should load random forest package. And we'll also build a decision tree model for comparison purpose. We'll also do a comparison of decision tree with respect to random forest, bagging with respect to random forest. Well, for bagging, you don't need a separate package. Random forest can well be used for bagging. So, tree is what is going to be used for decision tree model building, and random forest is going to be used for bagging and random forest. And we will use the dataset Boston, which is there in the package mass. So that's what we're also going to load. I'm going to show you how the data looks like. Well, the data you might be familiar if you have seen my other videos. I have taken this data many times. So the Boston data is a data of housing prices, the median housing prices in the city of Boston, and you have got the target variable as the median value of the house prices. It depends on many other things, the crime rate, the availability of tax rate, and many other variables. Okay, averages of population and so on. Okay, there are 13 predictors. Okay, 13 predictors. This one is the target one. Okay. Now we'll first build a decision tree model. Now, decision tree is a single decision tree, right? Single decision tree model. Unlike in random forest where you have, over 100 decision trees, it's just a single decision tree. Now, we'll see what is the prediction accuracy in this case. The syntax is simple. You are using tree and then target variable, and you are using all the predictors available to you. And the data is Boston. When you're building this model, we are interested in knowing what is the mean square error. Okay. Mean square is very similar to the residual mean deviance in this case, and is 13.55. Okay, so that's what the mean square error is. And we compare the different model using this matrix, because the one that gives the least mean square error is the best model, right? So it's 13.55. Just remember that. Now let's go to random forest. Now we can build a random forest using the function random forest, and we have the same target variable, and we're using all the predictor variables. However, we'll use a keyword called mtry, which is going to take randomly 6 out of them. So we have got 13 variables in total, and 6 out of them will be selected randomly. Okay, and that's the essence of building the random model, right? And data we're using is same, Boston. Alright, when we run this, we have the mean square error, right? Mean square error residuals is 9.5. So we had 13.55 by a single decision tree. Now we have 9.5. So that has surely gone down, right? So random forest has improved the prediction, okay, just by having more number of decision trees and averaging, we have been able to improve the prediction accuracy of the model. How many number of tree have been used? 500. If you do not use a number, it is going to use the default value, and the default value is 500, and you can specify how many you want using n tree. If you want more, you can use 1,001. It's going to take more time though, otherwise you probably get a better result if you're using more numbers. Okay, now we will do a comparison with bagging and random forest. Now we have seen that yes, random forest is now able to improve on the decision tree. Now the difference between a random forest and bagging is that in bagging the entire set of predictors is being used. In random forest there is a random selection of the predictors, so there is double randomness, right? In the randomness, is that going to improve the model accuracy? We'll just see with this data. Well, we cannot conclude anything because just by using two different just one data set we cannot conclude anything, but yes, we can just understand if that improves. We can take many number of data sets and see whether that is consistent across different data sets or not. So we'll use the same data set, Boston data, and we'll use the first one is a random forest model because you are using mtry, and the second one is a bagging model. Why? Because the mtry is the total number of variables. We are using all the predictors. Now remember, we talked about when m equal to k, it is nothing but a bagging. A random forest becomes a bagging model, right? So yes, so now we have this bagging model here, and we have got the random forest here. So the only difference is that random forest uses lesser number of predictors, and that uses randomly it takes from the list of predictors, right? Whereas bagging uses the entire set. The mean square error in this case is 9.5 in the random forest, whereas in bagging it is 10.6. So very clearly it's a win, right? Clearly random forest does a better job than bagging. But you cannot predict because the numbers are very similar or very close, right? So you can take different data sets to just verify if that works, but there is definitely going to be some sort of an improvement, if not substantial. Alright, so now we have understood the theory and the application of random forest and bagging or ensemble model in general. Now we have, I'm going to give a few assignments to you. This is the last part of the session wherein I've been given two assignments. I encourage you to send your assignments to me. You will find the email ID in the description section of this video. The first assignment is you split the data set into training and test data. Remember, I did not split the data into training and test data. That's ideally should be the way of building a model. Okay, so I encourage you to do that, and then compare the test error. We compare the training error. That's not the ideal way to compare two different models. So just compare the test error rate for a single decision tree with the random forest model. Now, if you're a beginner and you are not very familiar how to split your data into training and test randomly, and how to compare test error and so on, I highly recommend you to go some of these video in this particular playlist. I have a video on decision tree and bagging. Just go through these two videos, you will get to understand how do you do that. Okay, the second assignment is compare the test error rate for bagging and random for different data sets. So I've taken Boston, right? So you just take many of the data sets. We have got a data set called car seats and you can take a data set for classification. You can take a data set of any other data sets, like flower data is there, right? Alright, so these are the two assignments. The third assignment I would like to give is that we learned it for regression problem, right? You learned it for regression. Now you do it for classification as well. Just take a data set which has a target variable as a categorical data or a discrete one. So use a classification random forest and classification bagging and do the comparison. Okay. Yeah, so these are the three assignments you can do, and send it to me. The email ID is there in the description sections. Thank you so much.